Hello everyone, we are Team Greenlight District and we are excited to dive deep into our study What's the Difference? Electron versus Web, a comparative analysis of energy and performance in communication apps. Our presentation will flow through the following sections. Let's start off with the introduction. In today's connected world, communication apps are the backbone of remote tasks facilitating collaboration and education. This graph gives us a representation of how one of the communication apps we have studied has skyrocketed in popularity over time. The COVID 19 pandemic and the shift to remote work have accelerated this growth, making these apps indispensable. Electron, an open source framework revolutionizing the creation of cross platform desktop applications using web technologies, has appeared. It uses web elements like HTML, CSS, and JavaScript with native system APIs, creating a unified runtime environment. This unique architecture, as seen here, enables a smooth transition for web developers. As we can see here, Electron's popularity is not only soaring but shows no signs of slowing down either. While Electron thrives in the desktop space, web apps have their own charm, providing accessibility across devices via browsers. They are lightweight and user friendly. Our study pits Electron against these web apps, focusing on apps like Skype, Discord, and Slack to discern the energy efficiency and performance of both platforms. Why does it matter? With IT deeply intertwined with almost every industry, its energy imprint is substantial. Software, an underexplored facet, holds potential energy saving opportunities. Communication apps, being essential for digital interaction today, if optimized, can significantly cut down our digital carbon footprint. This research aims to guide users and developers towards energy efficient choices. Research significance. Our study is at the intersection of software development, energy consumption, and user experience. By unearthing the energy and performance profiles of popular communication platforms, we provide developers with potential insights to build efficient software and empower users to make informed choices that align with sustainability goals. Related work. The landscape of energy efficiency in software is vast. However, most studies fixate on mobile ecosystems or broader energy considerations. Few tread into the territory of electron versus web apps, leaving a gap in insights which our research seeks to fill. Our experiment is structured using the goals questions matrix approach. Let's break it down. Goal to analyze electron based desktop apps and their web app counterparts for the purpose of evaluation with respect to their energy efficiency and performance from the point of view of users and developers. Questions. We have divided our questions based on energy and performance, but essentially what we want to evaluate is how the duration of a meeting affects energy efficiency and performance individually in both platforms and how the mode of interaction affects the energy efficiency and performance individually in both platforms. Metrics. For energy, we calculate in joules, considering power in watt and time in seconds. Performance metrics include CPU utilization in percentage, memory utilization in percentage, and network usage in amount of TCP and UDP packets sent and received. And continuing this, let's explore the planning and design of the experiment itself.
So next is the experiment planning, which we have between two subjects, which is Electron and web-based. So for the browser that we're gonna use to test or doing this experiment is Google Chrome because it's the most famous one and everyone use Google Chrome, right? We are looking at popular online communication platforms like Skype, Slack, and Discord. These platforms were chosen because they offer different interact methods and are widely used. The reason why we chose the platforms are first, presence of both versions. Each subject possesses both electron and web-based iterations, allowing for a direct and balanced comparison. Second is the multifunctionality. The selected platforms extend beyond standard messaging capabilities, incorporating diverse modes of interaction. And the third is interaction duration. These platforms enable interactions of varied durations, aiding in exploring the effect of prolonged usage on energy efficiency. So what kind of interaction will we use in our experiment? The mode of interaction is integral to our analysis, serving as independent variable to elucidate disparities in both energy consumption and performance between Electron-based and web apps. This variable encompasses a variety of interaction types. The first one is audio-only interaction. These modes solely involve auditory communication, focusing on the exchange and processing of audio data. The second one is video interaction. This mode encompasses both auditory and visual communication, requiring the simultaneous processing of audio and video data, which can be more resource intensive. The third one is audio with screen sharing interaction. This mode integrates auditory communication with the sharing of screen content, necessitating the processing of audio data along with dynamic visual content. And the last one is video with screen sharing interaction. This mode combines auditory and visual communication with screen sharing, presenting a multifaceted interaction scenario with diverse data processing needs. Each mode provides insight into how different interaction scenarios impact the energy efficiency and performance of the considered apps. Here is the summary table, which you can see that interaction duration are set at 2 minutes and 8 minutes to represent short and extended meetings respectively.
I'm going to explain about the scripts that we use for the experiment. So first we created a bot that it's going to be a clicker. It's going to click in the different coordinates of the screen in order to perform the different activities that we need to do, like open a meeting or set, screen sharing, microphone or video. We did this by creating CSV files that are going to contain these coordinates, and the bot is just going to read this CSV and perform the activity that it's needed. As well, the bot receives a CSV file with the iterations that needs to perform, like the different configurations that each meeting has. We created as well two scripts for virtual microphone and virtual camera. We're sending an audio to the microphone as an input and a video as the webcam that is going to play during the meeting. That way, we're gonna make sure that the camera and the audio are gonna be the same for all the iterations. Now I'm going to explain you a little bit about the code that we have. We created this bot that is going to click on different coordinates on the screen in order to automate the meeting. So this bot is going to start the meeting, is going to set the configuration, and is going to close the meeting, give some waiting time, and start the next meeting. So for that, we are using these CSV files in which we are going to say, okay, for starting the meeting for Skype, we need to follow these clicks, and the bot is going to give these clicks, and the meeting is going to be started in Skype. Same for Slack and Discord, and for the different functionalities that each has. Then we have the part of the iterations. This part is important because basically we're saying the bot what it has to do. In here we have the randomized iterations that needs to be done. So in here we're saying that we want microphone on, for as well we want the camera on, and we want the screen sharing off for 2 minutes, and for the application number 3. These iterations are going to be read by the bot, and it's going to be executed and measured through these commands that is going to open Power Jeweler and T-Shark to capture the data. As well, we have the virtual microphone and virtual camera, that basically we have the virtual camera for creating a video that is going to serve as an input of the webcam, and the virtual microphone is just going to be redirected as an output to an input.
So now we are going to be talking a bit about how we conducted the measurements throughout the experiment. So we already mentioned that we have 4 main metrics: energy consumption, CPU utilization, memory usage, and network usage. For each of these, we are going to mention the tool that we used to measure it and how we used it. So to start off, we have energy, and we used Power Jeweler for it. And it's a command line tool that works only on GNU Linux, and also only works with RAPL supported Intel or AMD processors. So in this experiment, we were limited to Linux and Intel processor because of that reason. It measures power consumption and also CPU utilization, which we will come back to later on. We use a few options while using Power Jeweler. So, for example, we have L for linear regression. We have A, which allows us to set an application name to monitor. For example, for the Electron app experiments, we have Skype, Slack, or Discord. And for the web app, we have just Chrome because the apps are running on Chrome. And we also give F to allow it to save the monitoring data to a file. It captures data continuously, so we stop it with a timeout after the meeting duration. And finally, we get the power and time values from it, which we aggregate into energy values. For CPU utilization, we also use Power Jeweler, and we get it in percentage and then average it over time. For memory, we use the Linux command line tool PS, which gives process information at a specific point in time. For this, we give it the C option, which is basically the name of a command, and it selects all the processes under that command name. So, for example, if we give it Chrome, it will select all the processes that are spawned from Chrome. And we also give it some output column options. In our case, it's process ID, PID, and memory percentage. And since it gives data at just one point, we loop it for the meeting duration within 1 second interval. Finally, we have T-Shark or Wireshark. So Wireshark is a network capturing application, and T-Shark is basically the Linux command line tool that works the same way. It captures network traffic. We don't display the data in the terminal. We do set the name of the network interface that we want to capture packets from. So in our case, it's the main Ethernet network that's doing all the communication. And we also give it a stopping criteria, which in our case is the meeting duration, and it will stop capturing after that. So we write all the packet data to a file and then we read it. And then with the display filter, we capture only the TCP and UDP packets in the packet data and finally have the total number of packets from that. And after collecting all the data, we did some pre-processing and cleaning, which goes into the next part.
After collecting the data from the experiment, three steps were performed. In data preprocessing, data was cleaned. In data analysis, different methods were applied to interpret the results. In data visualization, those results and the patterns were visualized with the help of graphs. Now we will discuss each step one by one. In data pre-processing, data was cleaned. We didn't get any missing values in our data. However, there were few outliers in memory and network. So the outliers were detected using the interquartile range method, and they were handled by replacing the values less than the lower bound with the lower bound and values greater than the upper bound with the upper bound. So we didn't remove any row which had the outlier value. Next step is data analysis, which start with the descriptive statistics. In order to answer our four research questions, data was categorized into different data frames. Like we can see here, for web 2 minutes meeting duration, the mean of the energy is 10.223, and for web 8-minute meeting, the mean of the energy is 41.17. Similarly, for all the scenarios, descriptive statistics were conducted for energy, CPU, memory, and network. Next step is normality checking, and it was checked by using the Shapiro-Wilk test and QQ plots. In order to answer our four research questions, Shapiro-Wilk test was run on 16 data frames. Data was categorized on the basis of two app types, two durations, and four modes of interaction. Hence, the test was run for all four dependent variables: energy, CPU, memory, and network. Hence, it was run 64 times. In order to further analyze the normality, QQ plots were used to show the distribution of the data. So out of 64 tests, only 16 plots showed the normal distribution of data. Since our data was not normally distributed, it was transformed using the Box-Cox transformation. The Box-Cox transformation results were again checked by the Shapiro-Wilk test. However, results showed that the data is still not normally distributed and only 18 data columns showed the normal distribution out of 64. Since our data is not normally distributed, we use non-parametric test Mann-Whitney U test. And in order to search and answer our four research questions, it was run 40 times comparing the 80 data columns. The p-values were obtained to check the hypothesis related to our research questions. To foster the integrity of test comparison, the Benjamini-Hochberg correction method was applied to the p-values obtained from Mann-Whitney U-test. The next step and the last step is Cliff's delta. To aid the comparison between data frames, Cliff's delta method was used for effect size estimation. In this table, we can see the group A and the group B. For example, the group A for Web 2 minutes memory is being compared with the Electron 2 minutes memory. And the Cliff's delta -1 value show that the web meeting for 2 minutes memory values are less than the Electron 2 minutes memory. The data was visualized using histograms, scatter plots, and box and Weiland plots. And they showed the different behavior of the results. The findings showed that the shorter interactions revealed negligible difference in both matrices, while extended duration brought to light significant differences in energy and performance efficiency. Specifically, Electron applications demonstrated increased CPU utilization during intensive tasks like video or screen sharing and were more energy efficient. In contrast, web application consistently exhibited higher memory consumptions and network usage.